Let's now look at one important application of the relationships that govern radioactivity. This involves the dating, or determining the age, of archaeological or geological samples. If an object contains radioactive nuclei when it is formed, then the decay of these nuclei marks the passage of time like a clock, half of the nuclei disintegrating during each half-life. Geologists affectionately refer to this as the clocks in the rocks, a description that would have made Dr. Seuss proud, no doubt. If the half-life is known, a measurement of the number of nuclei present today relative to the number present initially can give the age of the sample. According to equation 31.4, the activity of a sample is proportional to the number of radioactive nuclei. So one way to obtain the age is to compare present activity with initial activity. A more accurate way is to determine the present number of radioactive nuclei with the aid of a mass spectrometer. The present activity of a sample can be measured, but how is it possible to know what the original activity was, perhaps thousands of years ago? Radioactive dating methods entail certain assumptions that make it possible to estimate the original activity. For instance, one technique known as radiocarbon dating utilizes the carbon-14 isotope, which undergoes beta- decay with a half-life of 5,730 years. This isotope is currently present in the Earth's atmosphere at an equilibrium concentration of about 1 atom for every 8.3 times 10 to the 11 atoms of normal carbon-12. It is often assumed that this value has remained constant over the years because carbon-14 is created when cosmic rays interact with the Earth's upper atmosphere, a production method that offsets the loss via beta- decay. Multiple techniques indicate that the equilibrium value of the carbon-14 concentration has indeed remained constant for the past 1,000 years. However, further back, say 30,000 years ago, it appears that the carbon-14 concentration in the atmosphere was larger than its present value by up to 40%, and other techniques should be used for more accurate dating. Moreover, nearly all living organisms ingest the equilibrium concentration of carbon-14. However, once an organism dies, metabolism no longer sustains the input of carbon-14, and beta- decay causes half of the carbon-14 nuclei to disintegrate every 5,730 years. Radiocarbon dating is not the only radioactive dating method. For example, other methods utilize uranium-238, potassium-40, and lead-210. For such methods to be useful, the half-life of the radioactive species must be neither too short nor too long relative to the age of the sample to be dated. Here is a simple example involving the radioactive decay of uranium-238, in which the half-life for its alpha decay is 4.47 times 10 to the 9 years. Suppose you find a rock specimen that contains 40% of its original uranium-238 atoms. What is the age of the rock in years? To find this, we can use the decay equation we studied previously, which is equation 31.5. We first divide each side by n0 and take the natural log of both sides. Taking the natural log of an exponential just returns the exponent. Solving for the time t, we get the following. In order to solve for t, we have to find the value of the decay constant lambda, which is related to the half-life through equation 31.6. Furthermore, from the information given in the problem, we see that the number of nuclei remaining, n, is 40% or 0.40 times the number of nuclei initially present in the sample, or n0. Making these substitutions into the equation above gives us our final result for the time t.